since the first paper is already ready, so just please go ahead to pick up your video.
So hello everyone, my name is Anil. Today I'll be talking about my paper 341 and 143, Flow, Segmentation, and Surface Normals. This is a joint work with Anil Baslamisli, Thomas Mensink, and Theo from the University of Amsterdam. Objects in real world contain several different characteristics like motion, categories, or geometry structure. Each of them corresponds to different modalities in computer vision, such as optical flow, semantic segmentation, and surface normal. Very often, they are treated as single-task problems. In this paper, we are going to explore the relationship between these three modalities in scene understanding problem. Talking about optical flow, different objects can move differently. Thus, if we know the object types and boundary from semantic segmentation, we can predict with more accurate the object flow and flow boundaries. In turn, flow discontinuity corresponds to depth discontinuity. So from optical flow, we can reason about scene geometry structure. This could help predicting better surface normal. Surface normal provides geometry information. This information is particularly helpful to recognize object categories. In other hands, geometry information is invariant to lighting conditions. Thus, for optical flow, this could help us to overcome the problem of lowly seen or strong cast shadows. For segmentation, we can somehow recognize the objects based on their motion patterns. Thus, knowing optical flow, we expect that semantic segmentation can also be improved. And finally, objects of similar types may share similar shape. By knowing object categories, surface normal could also be improved. In this paper, we studied the mutual interaction between the three modalities, the impact of their combination in scene understanding problem. To assist the process, we also designed a large-scale dataset of synthetic nature scene with dense annotation of various modalities. We take a modular approach in our study. We learn each modality separately using baseline network, and then refine them jointly without using RGB information. In this way, the refinement network has no access to real information from RGB images and can only learn from the supply modalities to improve or deteriorate the results. The diagram shows an example of refining two modalities. The refinement network receives a predicted modality and one or two supplementaries at various scales to learn embedded features and combine them to refine target modalities. The supplementary modality could be crowd truth. In this case, we will exclude it from the target to be refined. The scale box receives different modality inputs, scale them down to the corresponding scale, and learn the features, and then upsample them back to the original size. We also explore single-task refinement, where we have only one input branch, one output branch, and multitask refinement, where the joint features are used at different coupling level. Large-scale datasets with both optical flow and surface normal ground truth are hard to obtain, because it's not intuitive for humans to manually come up with pixel-wide annotation for these modalities. So in the paper, we stick to synthetic dataset. The first dataset is Virtual Kitty, a synthetic dataset designed after the famous Kitty dataset. With 20K images, we convert the depth ground truth to the surface normal. The second dataset is a large synthetic dataset featuring nature scenes such as gardens and parks. We present to you the UVA nature dataset. The dataset features nature scenes in different lighting conditions like clear sky, cloudy, overcast, sunset, twilight, and we have also random background. We also provide with the dataset multiple data modalities such as RGB images, semantic segmentation, flow, surface normal, depth, albedo shading, and even point cloud. Here are some statistics. We have 300K images in 60 garden models, each of size 12 by 12 meter, and the dataset is rendered in by physics-based planar cycles engine. We also use part of the datasets in our paper at CCCV this year. The first experiment is refining optical flow using semantic segmentation or surface normal. The first two rows show oracle experiments, where the supplementary modalities are ground truth, and the next two rows show refinement with predicted modalities. The RGB images are shown for reference only, and they are not used in any experiment. The second column is the baseline results, and the last column the expected crowd truth. We use flow netSys as a baseline for optical flow. The refinement results seems to beat all the baseline results. For Arco experiment, surface normal helps the most because geometry structure is rich and helpful for optical flow. The predicted surface normal, in other hands, are quite noisy, and we will see later. That messes up with the cues and kind of hurts the results a little. However, in both cases, the refined flow appears sharper with better details, for example, the lamppost or the tree leaves. For segmentation, again, the first two rows with crowd truth and the next two rows predicted modalities. The baseline network is resonated with additional decoder layer for full image resolution. The refinement is isolated from RGB images, so it can only learn from the supplementary modalities. In this case, optical flow or surface normal. These modalities help recognize objects with fine structure such as fence wire or the lamppost. However, they do not contain enough semantic segmentation to recognize different terrain types. Hence, the wrong blue regions on the grass cannot be fixed, although they do shrink a little bit. In the case of predicted supplementary modalities, due to uncertainties and noises in the prediction, the refinement contains more errors and sometimes hurt the performance if you see in the predicted flow, but visually inspections still show a better structure of thin objects. In the case for surface normal, the baseline mark revisited was trained for indoor scenes and objects that does not perform very well for driving a nature scene. Yet with the supplementary modalities, namely optical flow and segmentation, the refinement network can still recognize the geometry structure of the scene, like the crowd, the building, the trees, the fence, and so on. Regarding single-task and multitask refinement, we experiment with two modalities, segmentation and optical flow. The best results are for single-task refinement. The difference between single-task and multitask are not much in case of optical flow, but severely for semantic segmentation. If we try to refine both optical flow and segmentation at the same time, the segmentation will get worse, even worse than the baseline. As semantic segmentation requires recognizing correct class for each pixel, the network has difficult time if both inputs are noisy because they are predicted. The consequence is less severe in case of the type plus the last column, which extend the type architecture end-to-end and using RGB images. In conclusion, the paper analyzes the potential in combining three important modalities in computer vision: flow, segmentation, and surface normal. Different modalities contain different types of information and can provide complementary cues to enhance each other. In current study, the modalities are fixed to one predicted result and refined while being isolated for RGB images. But in future study, we like to include end-to-end training of modalities to exploit raw images features. Thank you very much for your listening. Okay, so the project, the paper is done within a Dreampod project where we have a robot going in the garden and providing together, we have multiple modalities. Like we can also recognize, because it's a robot moving in the garden, we can also have optical flow, and we can also kind of reconstruct the 3D point cloud of the garden. So we have both geometry and surface normal and optical flow and semantic segmentation because we want to recognize different objects in the garden. In this way, we can also assist our study within the project as the combination of different modalities. Currently, we are not investigating on that, but we just want to study the combination of different modalities. But yeah, speed is also one of the very important factors, and maybe in the future we will also put more attention into that for better application results.
Any more questions from audience? Okay, if there's no question, let's thank Speaker Gun.
Okay, thanks. So I believe the second speaker is from Toshiba Research. Okay. So he's going to talk about exactly what in the object. Please go ahead.
Yeah, very good afternoon. My name is Rudra Poudel, and I'm going to present to you a paper called ContextNet, Exploring Context and Detail for Semantic Segmentation in Real Time. This work has been jointly done in Toshiba Research Lab, in the Cambridge Research Lab, with my colleagues Ujwal, Stephan, and Christopher Jack, who should be somewhere here. Yeah. We kind of, as a community, agree that real-time perception is critical for autonomous system. Because what I'm seeing in the scene and where are these objects is very critical for the decision support system of those autonomous systems. So what is the problem then? Current state-of-the-art methods, they do very good on semantic image segmentation task. Normally, you get around like more than 80% accuracy. For example, like deep lab or pyramid scene parsing networks like PSP nets. But the bad news is that it takes more than 1 second just to segment 1,000 by 2,000 pixel images, which is roughly 2 megapixel images. So accuracy is really good, that is good. But the bad news is they are really slow, 1 frame per second. It's not good for the autonomous system. What else we observe in our literature is this. Going deeper or adding more layers improve the accuracy. As Abhinav Gupta also yesterday in tutorial, he highlighted that. The second thing we know from like 30 years back or 40 years back is fusing the information in a multiple level or from multi-scale information fusion is beneficial for segmentation, like pyramid scene parsing and all those pyramid architecture and all those things. But what is the downside of these two things? The downside is increasing cost. What is the meaning of increasing cost for us is floating point operation, memory usage, and power consumption. Because these three things is holding us back to use our system, our useful system, I would say, in like embedded devices. So in this work, this is our hypothesis. Let's back to the very basic of the computer vision. We know for the segmentation, what information means what is there in the scene is quite important, and where are they is quite important. So this is our aim. Can we learn these two informations independently? Because the kind of information needed for these two tasks is quite different, which I'm going to explain you later. Means can we do that things and achieve a real-time system in embedded devices? That is our aim. So let's go to. So this is our proposal. So what we want to do is we want to learn what is there in the scene using a context branch. We call it context branch, independent, kind of, not really independent, kind of. And we want to learn where are the object, means boundary information, independent. And together, we want to merge this feature nicely so that we want to get a real good semantic segmentation result as well as a real time. That is our challenge, and this is the proposal. Let's go to the detail. In our context branch, we want to know what are the objects in the scene. Means we want to see high field of view, but we don't need high resolution. But to learn what is there in the scene is a very complex task. It has a complex feature correlations. Means we need many layers. But the good thing is, we don't need a high resolution images to learn this information. Means we can learn these things on very small resolution images, like 1/4 or 1/8. So in this way, you can still reduce the cost. So this is our context branch. And in the detail branch, we don't need to know the boundary. We don't need a large field of view. We need a small field of view, but we need a high resolution images. So we want to learn these things in a high resolution images, but we just need a very small field of view. Means we don't need a many layer, just 4 layers. We use just 4 layers. 3-4 layer is fine. So we just use 3-4 layer. And together, we merge, we add features, not output, yeah? It's just a visualization of the branch. I'll tell you later. We just add these 2 features together, and we learn end-to-end model. So the benefit of this is we reduce the computational cost a lot. I'll come to that later. But I just tell you the nice theory, right? But does our model really do the things I just said to you? To visualize these things, we have added 2 auxiliary laws in 2 branches. So we have a loss, we have a loss in the branches. These 2 branches, we have auxiliary loss. And this is the visualization of our auxiliary loss. You can see, here you can see in the context branch, the person is correctly classified, but if you see the leg, the boundary is not nice. But in the detail branch, the leg is nice, but if you see the body part is missing. Together, you see in the both branches, the ContextNet branch, you get a nice person. Similarly, if you see the sky, because you need to see the larger part, then ContextNet is, context branch is doing good, but the detail branch is not doing good. But interestingly, it is capturing the boundary very accurately than context branch. Together, you can see in both branch, we got a better cloud. This is more interesting. If you see in the context branch, the terrain is correctly classified by the context branch, but it missed the boundary, these small poles. But if you look at the detail branch, it correctly classifies the poles, but it missed the terrain. Together, it knows how to merge it, because we have a merging one convolution, right? The merge model is there. So if you see there is a merge model. So together you see the context branch is combining this information nicely. So I believe, or I think we believe, I think I convince you that whatever I said, our network is somewhat doing these things. So let's go to the detail in the network design. So we utilize the depth-wise convolutions for our network to reduce the number of operation and all those things. The reference is there. So another question raised, how many those branches you can use? Can I use more than 2 branches? Can I use more than 3 branches? Can I use different resolutions? There are lots of questions you can ask. So we did some evaluation studies, and you can quietly see the ContextNet CN14 quietly balanced between the other branches. If you see ContextNet CN124, that is down, which is quite accurate but really slow. So means adding more layers, this is the conclusion. Adding more layers, you will increase the accuracy, but you will reduce the cost. Another interesting point I want to point it out here is that our ContextNet, just using 1060 parameter, we can achieve almost 58% accuracy in cityscape dataset. And that accuracy is, if you remember, 3 years back, state of the art in a cityscape from the deep lab, right? So that's quite good news. So another interesting thing we used, the component for our ContextNet is a pruning. You study the wider network. The idea is you want to reduce the computation, but similar accuracy, so you get a Skinner network. That's a pruning. But recently there is an interesting paper called lottery ticket hypothesis. You have a more lottery, you have a more chance to win. So we know ContextNet has a less than 1 million parameter. We have a quite low capacity, means we don't have enough capacity. So what we did is, we were getting like 65% accuracy. Then what we did is double the number of features. We got a 68 around. Then we prune it. We still achieve very similar result, So in result of that, unlike other pruning strategy, we use the same strategy but in a different context, and we improve 2% or 2.5% using this pruning strategy. And this is our quantitative results. If you see here, I told you, like PSPNet is fast than like other state-of-the-art method, but it still is less than 1 second. More than 1 second for large images. But accuracy is quite high. But if you see our ContextNet, accuracy is slightly low, but we are almost 25, 30 times faster than PSPNet, right? So if you see, there are only two methods exist, eNet and ContextNet for the real time for 2 megapixel images, and compared to eNet, we are almost 10% better. So I think I convince you that ContextNet is one of the fastest semantic segmentation model we are proposing. So these are the few results, and I would just want to highlight here is two things. We use very old Titan X because we need to compare with other results, and still we are getting 23.2%, 23.2 frames per second, and our number of parameters is less than 1 million. So this is the video. So you can see the video. Yeah, there are some flickering because this is a frame-wise. I mean, I must admit that we are accuracy-wise, we are still like lag behind like PSPNet quite a lot, like around 10%, being honestly saying. But it's still good, I think. It's still like for the autonomous system. Okay. So in conclusion, what we proposed is learning the global and local context separately. Doing so will reduce the cost, because for the global context, you don't need a high resolution. For the local context, you don't need many layers. That is the key. So using this insight, we achieve the real-time system and the competitive accuracy. And interesting, maybe it might be interesting for many people, like even in NVIDIA Jetson, that at a tiny GPU, low-power GPU, we can achieve more than 16 frames per second for 2,000 into like 1,000 pixels images. And our pruning strategy increases the accuracy. And the limitation is still we have some gap to catch with the state-of-the-art semantic segmentation model. Thank you for your attention.
Okay. Any questions? Okay, no question. Okay, probably. I have a short question. If I understand correctly, in your framework, you have actually two branches. So what are the actual procession going in these two branches? Is it kind of convolution or?
Yeah, convolution.
So how do you need to synchronize these two branches?
Actually, very interesting question, because in the beginning when I thought we have two branches, how do I merge these features? I mean, I had that doubt, but for some reason the gradient descent just works. If you upsample this feature map from this lower branch, you do the bilinear upsample. You just need to make sure that number of feature map from this last layer and this layer is same. And if the number of feature map is same, and if you upsample, bilinear upsample, we just did simple add. And if you do end-to-end optimization, it works. So you don't need to do any other fancy things. Just one constraint is they need to be same dimension. That is. And another important thing I forget to mention is it is not pre-trained on ImageNet. So probably if we train on ImageNet, we didn't have a time. So if we do that, probably we might improve also accuracy.
About the pruning, what is the big idea behind your algorithm?
To be honest, I don't have much idea over there, to be honest. What we did is we use the pruning. Like you have a big network, you prune, means you reduce the cost, but you maintain the accuracy. So that's what everybody doing. But our model, I think our situation is, we are lucky that our situation is, our model is really underfitted because less than 1 million parameter. So if we prune on that, we are not able to prune anything. And the new paper, which I mentioned, like lottery ticket hypothesis, if you have a more lottery, more chance to win. So what we did is we double the number of feature map, we increase the accuracy 3-4%, and we prune, still we maintain that accuracy. So we just apply this pruning in an interesting way in our problem.
Great, thank you.
Thanks. Thank you.
No other questions?
Okay.
Okay, let's welcome our third speaker from Adobe Research to just talk about the attention module.
Okay. Thank you for the introduction. Good afternoon. I am Jongchan Park from Lonip. This work is done while I was at KAIST in collaboration with Sanghyun Woo, Dr. Joon-Young Lee, and Professor In-Sok Kwon. The title is Bottleneck Attention Module, or BAM. It is a simple self-contained attention module for any CNN architectures. So let's begin from the intuition. So when an image is given, we tend to focus on the relevant parts of the image. So for example, if you're seeing this image and you're driving, then you must focus on the road parts rather than the beautiful scene on the other parts of the image. So I am not an expert in brain science, but they say there is an attention mechanism in human brains at the bottleneck regions. So we can focus on the relevant information rather than the irrelevant information. But when we look at the deep CNN architectures, we do many convolutions on the input images and features. So we treat every data points equally. So the output is usually very noisy. So we thought we can implement attention mechanism to help the network to focus on important parts of the image. So the key idea is to emphasize important parts and suppress less important parts. In CNNs, information is contained in the form of 3D feature maps, so we produce attention map for the feature maps. For example, an image is given to the CNN, then feature map, intermediate feature map is produced. This is a visualization of the intermediate feature map. We just averaged over the channel dimension. And this is kind of noisy. There is a lot of activation from the monkey itself, but there are noisy activations from the tree also. So we generate an attention map. This is also just averaged over the channel axis. And the final refined feature map focus more on the target object and just ignore the rest of the background clutters. This is another example from ImageNet. This is a result from vanilla ResNet 50. The last feature map from the network is very noisy, and it say it's an acorn. Actually, this is, if you look carefully, this is a baseball. So when we use attention, the network can pay more attention to the target object, and it correctly classifies it is a baseball. So we want to make the network to focus more on the target object. Attention mechanisms are used in various areas. A famous example would be the show attend and tell paper. The authors used attention mechanism to extract features to generate the for caption generation. And attention is also widely used in VQA, and sometimes it's used for general classification tasks. So why are attentions are used in those areas? We thought there are two reasons to use attention. The first one is performance boosting. So there are two parts of the performance boosting. The first part is forward denoising effect. As you've seen in the previous examples, there are feature denoising. We can refine the feature maps to focus on the foreground object. And in the backward path, we can train the network to focus more on the relevant part, because the attention mask is multiplied onto the convolutional activation. So in the backward path, the more gradient will flow into the relevant part of the convolutional feature. And the second advantage, I would say, is it's more interpretable. We can see where the network is focusing on. So we know when and how the network will fail on some tasks. So let's jump into our proposed module. So as I said, we try to refine feature maps in between convolutional layers. So this is an example of the feature map between convolutional layers. So in our module, we want to generate an attention map with the same size of the feature map. So this attention map represents the importance of each element in the feature map. Then we multiply the attention map with the feature map. Then we have the refined feature map. So while designing the module, we have considered two factors. The first one, we wanted to keep the module simple and lightweight. If the design is too complex, nobody in here will use the module, so the idea would be useless. And also, it should be lightweight, because if the new module introduces much more overhead, then there are many other alternative ideas to try. So we wanted to keep the module simple and very lightweight. And also, if you design a small module, you have to decide where to put the module in. So you can infer from the paper name, we put it at the bottlenecks of the network. So what is the bottleneck? So it's known that in human brain, the quantity of information is reduced during attention process. So in CNNs, quantity of information is reduced in the pooling layer. So we say this region is bottleneck of CNNs. So we say pooling layer is the bottleneck of the CNN. So we put the attention module before pooling, before the information loss occurs. So we put the modules at each bottleneck of the network, and I'll talk about the detailed design of the module. So we are going to make an attention map as the same size of the input feature map. But most intuitive way would be encoder-decoder architecture to generate a 3D size, equal size map. However, it can be very expensive. So we might need several GPUs to train the network. So we have to find an efficient way to design the network. So we propose to factorize the 3D attention map into two parts. The first part is channel attention. The second part is the spatial attention. Intuitively, spatial attention focuses on where the important parts are. And in case of channel, as we consider each channel is a feature detector. So channel attention means what we should focus on. This is the detailed design of the architecture. In the channel branch, we aggregate the feature by global average pooling and use two-layered multi-layer perceptron to get the channel attention. This is a 1D channel attention map. And in the spatial branch, we use 4 convolutions. This is very lightweight because the channels are reduced. And 4 convolution layers to get the 2D attention map. And we expand the 1D channel and expand the 2D spatial attention to make and add them together to generate the 3D attention map and multiply it with the input tensor. Yeah. And during MLP and convolution, we reduce the number of channels to save parameters and computations. This is a design hyperparameter called reduction ratio. And also during convolution, we use dilated convolution to aggregate the spatial contextual information. And dilation value is also another design hyperparameter. We explore this experimentally through ablation studies. So this is the final design of, this is a visualization of how our module works. So we put the module in between every stages right before pulling. So, and you can see the feature map is iteratively refined to focus on the foreground objects. Yeah. So this is a part of our ablation study. All the results are on CIFAR 100 classification, top 1 error. We use ResNet 50 as our base architecture. In the left table, we experimentally find the optimal settings for channel reduction and dilation value. Dilation value 4, we found it's the most, the best value, and we find reduction ratio 16 is a good value to work on. On the right side, we explore the effect of channel and spatial branches separately and how to combine those 2 branches. As you can see, there are more improvements when we use them together. There are some synergies from combining the channel and spatial attention. And the best way to combine 2 branches is by summing them together. We tried max or multiplication, but adding them is the best option. This is the results in CIFAR 100 classification. There are ResNet 50 and ResNet 50 plus BOM. You can see the overhead is very small, like 1% or 2%. But there are clear improvements in performance in every architecture. But CIFAR 100 is very small, so we tried on ImageNet. In ImageNet, the overhead is still very small. It's like 1% or 2%, and there's also clear improvements in performance in every architecture we tried. You see that BOM gets higher performance with negligible overhead. And we thought it can be very useful in mobile-oriented settings. So we tried our module in mobile-oriented architectures, in MobileNet and SqueezeNet in various settings. The overhead is still very small. It's like, 2% at most. But you can see there is huge improvements in the performance. So, yeah, it's very effective. So this module is very useful in classifications in various architectures. But the question is, can we use this module in other tasks, such as detection? So we tried on MS Coco. We used BOM in the feature extractor part. You can see there is a clear improvements in the MAP. And we also tried on VOC 2007. We tried our module in the decoder part. And you see it's also improving the performance. StairNet is a variant of SSD, and we implemented BOM in the StairNet. So BOM is useful in classification and also useful in the detection task. So in conclusion, we have proposed a lightweight and easy-to-use attention module. We can use it in various tasks and in various architectures. BAM improved performance in negligible overhead, so it has strong potential in mobile-oriented settings. We can also extend the usage to other tasks, but we have not enough time. So if you are doing other tasks, I will recommend you to use using in other tasks. And also, we have a next version of our module called CBOM. CBOM is still very lightweight, but it's more powerful. We did many more experiments on this paper, and it will be presented in ECCV next week. So if you're interested, visit us next week. So, yeah. Thank you for listening, and if you have any questions, just please ask me now.
Okay. Any questions? Please.
If you go back to your schematic drawing, then you multiply the output of your
Wait, I think it's this one, right?
yeah.
Okay.
Thanks. Thank you for your talk. Here you multiply your attention with the input tensor, but then also add the unmultiplied input. Why do you do that?
Oh, okay, that's a good point to ask. Actually, there is a prior work called Residual Attention Network in CVBR 2017, and they used such a way to add an attended feature map on the original feature map. They also did this way in this way too, and we tried not using the skip connection, and adding the skip connection showed better performance. So we just kept this architecture. Yeah.
Do you have any idea why?
I think the important factor is that the gradient flow. I think the gradient flow is the most important. I think it follows the same philosophy with the residual network. Yeah.
Thank you.
Thank you.
Any more questions? Again, probably I have a quick question.
Okay.
We saw that you insert your attention model into some computer vision tasks like detection and also classification. So did you really test your attention detection?
What do you mean by attention detection?
Yeah, like saliency pixels. How did you evaluate your attention?
Not in this paper, but in the next version of our paper, we did some qualitative evaluation, some visualization of the attention map. So we want to the attention helps the network to see larger extent, the full extent of the object. We did some experiments on investigating such a thing, but we did not investigate directly on the attention map itself. It's kind of hard to analyze the attention map itself. So, yeah. Okay.
Presentation from UCL London.
Thank you for the introduction. The work I'll present today was carried out in collaboration with Tobias Ritschel, Tim Vagi, and Niloy Mitra. In this project, we worked on a novel approach for handling boundaries in convolutions. Convolutional neural networks have become the standard in many computer graphics and computer vision applications, and so exploring potential improvements at the architectural level has become extremely relevant. In this work, we specifically focus on the core of all these architectures, which is convolutions. Let's begin by explaining how boundaries are currently being handled in convolutions. We commonly refer to convolutions as either valid or sane convolutions, based on how the boundaries are handled. In valid convolutions, no additional padding is provided. This, of course, type of convolution leads to a reduction in the size of the output, as we cannot convolve the kernel at the boundaries. Clearly, in state-of-the-art architectures, this would quickly lead to a massive loss of information. In the case of 3x3 convolutions, at each layer we lose 2 columns and 2 rows. To avoid this issue, we more commonly use what we refer to as sane convolutions, where we instead use padding to preserve the original size of the input.
Again, in the case of 3x3 convolutions, we would add two rows and 2 columns. Using sync convolutions, though, we encounter a different problem. As the weights for a specific kernel are learned, the same kernel is actually applied to the whole input. This includes the boundaries, where the padded values are not necessarily consistent with the rest of the image. As a result, as the kernel parses the boundary values of the input, we are introducing a bias, and we get biased values in the output, and successively propagated through the whole network. In our simple example, using our output as input to a second layer, we would already have over 95% of the output being biased. In real scenarios, while we have way more pixels to work with, we usually downscale the input several times, so the biased values are propagated either way. So let's now see an example of why this is a problem. Let's imagine that a specific kernel of a network, here in blue, is trying to identify some feature in an image. If we actually knew how to extend the original image past its boundaries, we would get an ideal response with no error. But what if the original image was zero padded instead? The observed response would be biased at the boundaries, as the filter would not be able to correctly identify the feature there. While reflect padding would work for horizontal or vertical features, it poses the same exact problem when you have diagonal or simply less straightforward features. And the same happens when you have any other type of static padding method. As we mentioned, the bias which is introduced at each level is also going to be propagated through the entire network. We argue that in order to limit this bias, the filter responses at the boundaries could instead be learned. Specifically, we could learn additional kernels for each of the boundary cases. In the case of 3x3 convolutions, this would be the 4 edges and the 4 corners. While this approach would not scale well with the size of the kernel, the state-of-the-art architectures are almost exclusively comprised of kernels of size 3 or less, so this is not necessarily a problem. While this approach requires additional kernels, this would only be run on subparts of the input, thus not requiring substantially higher computation. In practice, we observe the overhead to be less than 1%. Let's now have a look at how this would work in practice. Firstly, the original input needs to be split into the components needed for each kernel. This would be the edges, the corners, and the centerpiece. The corresponding kernel is then run on each one of these subparts of the original input to obtain a partial output. To run the kernel on the input, the additional context is required, which can directly be extracted from the original input, which includes also the originally padded values. The difference is that the specific kernel is going to learn a response that is aware of those padded values because it is always and only being run on that specific subpart of the input. Once all the outputs are generated, these are merged back together, and the merged output can now be seamlessly fed to the successive layers in the pipeline. This means, for example, that if you really want to run some 5x5 convolution, you can simply treat those specific layers as usual and only use this for 3x3 convolutions. In our initial experiments, we tested very simple architectures, started with a single layer and 3 filters. In this test, we attempted to reproduce a specific 13x13 blurring kernel using 3x3 filters. We tested the results using zero padding, reflect padding, and our method, which is marked here as explicit. From a single layer and 3 filters, we gradually increased the number of available filters to the network. And then we repeated the experiments while increasing the number of layers available instead. Finally, we increased both at the same time. In all of these experiments, with the same amount of training, we obtained superior results with our method. Additionally, we observed how the standard padding techniques, especially under limited resources, were compromising the quality of the learned filters to mitigate for the error at the boundaries. We also tested a simple fully convolutional unit-like architecture for various tasks, in particular for Gauss filtering, for debayering, colorization, disparity, and scene flow. While we observed an improvement for each one of these tasks, the improvement was not even among the tasks. This is further demonstrated by the error height fields associated with each one of these tasks. These height fields represent the average error distribution for a specific task. As we can see for the Bayesian task shown here, we observe an improvement both at the boundaries and the inner part of the image. While for the colorization task, for example, we can hardly tell reflect padding and their method apart. We theorize that this has to do with the type of filters that each of the different applications require. Finally, we show the error maps for the Gauss filtering example, and once again, we can see an overall improvement both at the boundaries and in the inner part of the image. In this work, we try to show how a learned strategy for the boundaries can actually be useful. We demonstrated its effectiveness on image-to-image tasks where the quality of the output is more relevant. And an important note is that while all the experiments were carried out were fair in terms of the amount of training that was received, as the kernels associated with edges and corners are seeing way less data than their counterparts, they could probably benefit from a training procedure that actually takes this into account as well. Thank you for listening.
Any questions?
Well, not necessarily, because the problem is that, well, obviously they are more difficult. That's why I'm mentioning that it might be useful to show more data for the edges and corners. But it's not more difficult, because if you think about it normally in a convolution, when you're parsing the whole input with your kernel, you can't even try to learn it, because you have the same values for all the image. So the fact that you can learn additional information, it's always worth it. Well, this doesn't really work because basically if you want to flip the kernel, you're going to have some filters which will not work anymore. For example, say that you have this filter, diagonal filter, and then you flip it to learn it from the other side, you're going to have your filter that doesn't work anymore, right? So you actually need all of them, sadly.
Okay, probably I have one question.
Sure.
Could you please elaborate more about your training sets in terms of the
About
size?
what, sorry?
Your training sets.
Okay, so for the examples that you're seeing here, I've used ImageNet, basically the subpart of ImageNet that was used for the challenge that was used for it. It's about 1 million images.
So you
It was the standard 80-10-10 split.
Another question, probably.
Sure.
Could you comment on your complexity of the algorithm?
So in terms of complexity, the overhead is very small because basically you're not running the additional kernels that you have, you're not running them more than what you would run a standard kernel because you're decomposing the image and running on every pixel only one kernel. You obviously add a little overhead in terms of memory, but it's irrelevant compared to other overheads in memory that you have normally. So I would say that there is not much overhead. What we also have a section in the paper explaining how we computed the overhead, but basically it's about 1%.
Okay, let's thank speaker again.
Thank you.
we should have the next paper from Zhejiang University, China. Number 5.
Okay. Hello, everyone. My name is Haoji Hu from Zhejiang University, China. This work is collaborated with two of my students, Huang Wang and Xunmin Zhang, and another is my colleague, Yuehai Wang. My paper, the name of my paper is Structured Probabilistic Pruning for Convolutional Neural Network Acceleration. Firstly, we need to see why we are going to do the convolutional neural network or CNN acceleration. It is because that convolutional neural networks requires high memory storage and massive computation. We need to reduce its memory storage as well as the computation. For example, for VGG, it cost us 1.7 seconds to process one image for my laptop. So there is a problem. How to reduce the complexity of computation while maintaining the performance of CNN. So previous work indicated that there are several levels of convolutional neural network compression and acceleration. The first level is the network architecture level, which is to design very small network to do the regulation or detection task. In recent years, there are some networks such as SqueezeNet, MobileNet, ShuffleNet. They are all small networks which require less computation. The second level of compression and acceleration is the layer level. The layer level, we try to use matrix decomposition to decompose a big matrix to multiplications of several small matrices, so that reduce computation. And the third level, which we focus in our paper, is the weight level. The weight level means that we try to eliminate some weights in a network so that to save computation. And the last and the smallest level is the bit level. The bit level, we try to do some quantization to do encoding of bits to further reduce its storage. So that's 4 levels, and our work focuses on the weight level. So this is a conception of structured pruning. The pruning means that we try to eliminate some weights in a network. And what is structured pruning? The structured pruning should be like this. For example, at the top is a big convolutional kernel, and the white squares means that some weights which is close to 0, so that we could eliminate them. If all the zeros are distributed as very irregularly, even if we could obtain such kind of kernel, normally we cannot deduce the computation because we still have to do the whole convolution for all networks. But if the zeros are distributed very regularly or with some structure, such as a bottom one, so that we could decompose the convolutional layer, a big convolutional layer, a big convolutional kernel into 4 very small convolutional kernels, so that we could save computation. So this paper we are doing structured sparsity. Specifically, we do the column-wise structured sparsity. And this is our our contributions for this work. Well, normally the typical way to do pruning is like this. Firstly, we tend to prune unimportant weights or weight groups, which is the columns in our paper, and then retrain the whole network to regain accuracy. Then a problem arises: how we can measure the relative importance of different weights. The literature has proposed several measures, such as L1, L2 norm, or first or second order gradients. It is hard to conjecture some once-for-all mathematically sound criterion because first, the relative importance measure is not very reliable. The second, the relative importance probably changes during training. So we propose SPP, structured probabilistic pruning, which prunes weight groups in a probabilistic manner. For each training iteration, we assign a pruning probability to each weight group. For example, 0.5 pruning probability of a weight group means that during this time, there are 50% chance to prune this weight group, and 50% we retain the weight group during this time. Then we control the probability, this probability based on importance criteria, which is one of the previously there one or two norm or first or second order gradients. Then if at some time the weight group is important, then we decrease its pruning probability, and if it is unimportant, then we increase its pruning probability. We only permanently prune the weight group when its associated pruning probability reaches 1. So the previous pruning, which we call deterministic pruning, it just pruned the weights once for all. But our pruning is probabilistic pruning, just like to increase or decrease the pruning probability, and finally we got everything pruned. There is one metaphor about this. Previous pruning is like students take one single exam, and we need to decide who are good students or who are bad students. But SPP, our method, is like students take several exams, and we measure their performance accumulatively to decide who are good and who are bad. The details of the algorithm. Firstly, we sort weight groups by the importance measure. The higher the rank R, the more important the weight group. And the delta is the increase of pruning probability for training iterations. We arbitrarily assign increase of pruning probability based on the rank. There is several settings of functions between rank R and pruning probability increase delta. A linear function is the simplest, but we validate functions with curves are more suitable. We find that weights are distributed like Gaussian, so there are many weights take similar values at middle ranks. We must make the curve flat at middle ranks and make it steeper at lower and higher ranks to catch up the changes of importance criteria of the weights. We reduce in our paper a continuous function to achieve this. Please see our paper for details. It is very simple for the algorithm. Firstly, we generate pruning probability with the above method. Then we generate a mask by Monte Carlo sampling of these probabilities. Then we apply this mask during forward calculation and back propagation. And after several iterations, we recalculate the pruning probability based on this diagram, and then we do the same thing again. until some part of the pooling probability reaches 1. So we permanently pooling some part of these weights. And some other issues. Firstly, when to pool, we find that different pooling intervals generate similar performance. So we choose smaller pooling intervals, like, for example, like 90 iterations. So the 90 iterations. We find so that we could save time if we choose smaller pooling intervals, and we choose we set the pooling ratio, which is the pooling ratio. Pooling ratio means the proportion of weight groups to be pruned of each layer by PCA analysis, which is like a previous paper. Okay, this is the result. The result should be firstly, for example, if we see that there are several popular nets like AnexNet, VGG, and ResNet, and if we speed up 2 times of AnexNet, then for our method even increase the accuracy. And it could be seen that our method performs in most of times our method performs the best compared with other 3 methods. Our algorithm can also do transfer learning. Here we do transfer learning on CafeNet, on Flower 1 to 102 database. And we find that compared with another method, in different speed up ratios, our method could achieve less increased error. And there are some discussions. Firstly, did SPP, our method, really correct misjudgments at the beginning of the pooling process? Yes, you could see from this graph. This is the CONVNet on CIFA10, and the x-axis is the speed up ratio, and the y-axis is recovery ratio. Recovery ratio means that the weight groups which is below the threshold rank at the beginning over the number of total weight groups. So normally you could say for different speed up ratio, approximately 10% to 30% 10% to 30% weight groups are recovered finally. So our method is not sensitive about hyperparameters. There are only 2 hyperparameters for our method. And you could see that in a reasonable range of these 2 hyperparameters, our accuracy is normally similar. So here is a conclusion. Firstly, we propose a probabilistic and progressive structured pruning method, which can prune weight groups efficiently and effectively. And compared with recent method, SPP delivers encouraging results compared with the existing state of the art. Third, SPP's performance also translates to transfer learning tasks in addition to canonical classification tasks. Fourth, what the SPP removes may shed light on what's the effective parts of CNN filters. Thank you very much, and questions are welcomed.
Okay, questions? Okay, let me give a start. So did you have statistics like layer by layer? How many weights are put to 0 after your pruning algorithm, and what is the trend for that? I mean, suppose you have a CN with 5 layers or 3 layers.
So how many weights are put to 0?
What is the percentage of
weights?
Yeah.
Okay. Normally in our paper we discussed this. The situation should be like this. We use, For example, we use the PCA to deduce how many, for each layer, how many weights we need to prove. For example, for the PCA, we use PCA to reconstruct we measure the reconstructed error of each layer. If the reconstructed error is very high, which means that in this layer it is not suitable to prove too many weights. So we set the proportion of weights according to the PCA. All the data are in this paper. I can't remember exactly.
Any other questions? Okay, let's thank speaker again.
Thank you.
Hello, everyone.
Please go ahead.
My name is Juan Manuel Perez Rua, and I'm gonna talk to you about our work that we have been doing in Orange Labs in France. It's entitled Efficient Progressive Neural Architecture Search. Well, and it's about neural architecture search. So let's go first by defining the problem that we are trying to tackle, and it's basically trying to find an optimal architecture for a given task, and the task is represented by a data set. In this work, we are focusing on classification problems, mostly the CIFAR-10 data set, but we consider the fact that most of the time advances in classification problems, they reflect well on different kinds of tasks. So this is what we are trying to do, basically optimize this function in terms of the score on a data set given by pairs X and Y. So we want to find the most optimal architecture F that belongs to a search space, a search domain, capital F. And of course, we want to obtain as well the parameters of the neural network F, but this is usually obtained in a block-based manner with stochastic gradient descent first on the parameters. Well, how to obtain F is what we are going to talk about now. At first, I would like to talk about the two search spaces that we use in this work, and most of the works of the state-of-the-art also use. So the first one is what is called macro space, and it basically it's related to designing convolutional neural networks in its full extent. And by that mean that we need to define the operation that you have at each layer and also where the input connections are coming from. So in the full CNN macro space, you have skip connections and operation at each layer. The second space we are going to be talking about today is the microspace. This is a bit more complex to explain. Basically, we want to design cells, convolutional cells that we are going to stack, as you can see at the bottom part of the figure. We're going to stack to form a full convolutional neural network. And each cell is composed by one or more blocks, 1, 2, 3, 4, 5 blocks. And what we are actually designing is the structure of those blocks. So each block can have two inputs, and those inputs might belong to a previous layer or to a previous block in the same cell. So that's part of what we are trying to optimize. The other things that we are trying to optimize is the actual operation that you apply on those two inputs. So there is a small example in here. A cell is conformed by two blocks, and the blocks are interconnected with each other and with the previous layers. But I would like to start talking about the progressive neural architecture search, which is basically the method from the state-of-the-art we depart from. Basically, they focus on the micro search space, where they define a convolutional neural network with a few layers, and then for testing it in CIFAR10 on ImageNet, they basically extend the convolutional neural networks with more layers, but with always with the same cell structure. We're going to be doing the same in the microspace. So at the core of the progressive neural architecture search, you find an optimization approach which is commonly known as sequential model-based optimization. In this method, basically you have a surrogate function that you are going to use to try to predict the validation, the score on a validation data set. So basically, the input of the surrogate function is a sequential description of the neural network or the block that I was talking about before, and the output is the score. So supposing that you have something like this, then you can explore the search space in a progressive manner. Maybe this is kind of the algorithm, but maybe it's better to explain it with a small example here. So suppose we are exploring the micro search space. You first start by listing all the possible architectures for the minimum level of complexity. In this case, an architecture that is formed by cells with one block. So basically, you take all of these neural architectures and train them all, and then feed them as a training data to the surrogate function. So basically, your surrogate function is starting to see how the search space works. At the next step, you basically unfold the complexity level. That basically means now you have another set of blocks. Now you have way more architectures, and this time you don't want to train them all. You want to ask the surrogate function what are the best K architectures that are given by the predictions that it's doing about the score. So then you use those to refine the surrogate function by training the surrogate function again with those real scores. And then you unfold again to the next complexity level. This process repeats until you reach all of the complexity, the maximum complexity level of your neural network. So this simple process actually is able to find good architectures. On CIFAR10, it finds an architecture with a 3.41 error, but it takes 1.5 days and 100 GPUs. That's because basically you are training a lot of architectures from scratch until almost completion. So that's not good. So it looks bad, 100 GPUs in one day, but actually that work was an advance on the previous state of the art that it was using around 800 GPUs and taking around a month to find a decent architecture. So PNAS, the progressive NAS, actually have a very good sampling efficiency. But it still requires a lot of resources, as I mentioned. So we want to do something about that. And the other problem is that exploration is very greedy. As I was explaining you start exploring the search space according to what the surrogate function is telling you, and that might be the best way when you have so few training data samples, which are the architectures that you train it on the minimum complexity of the neural network. So another element that we want to bring to this work is something that was proposed very recently in a paper called Efficient Neural Architecture Search. Basically, they propose to do weight sharing among sample architectures. That's a reinforcement learning-based method where they see the search space as a big graph, and each one of the nodes of the graph basically is an operation at a layer of the neural network. And the whole graph is basically a juxtaposition of all of the subgraphs that are representing each one of the possible neural architectures. So when you have that view, actually it's kind of easy to realize that you can share weights among those models that you are sharing among sample architectures. Doing that trick, actually they were able to reduce the search time of the previous reinforcement learning method from 800 GPUs in a month to 1 GPU in a day. So that's quite an improvement. Since that, we found that progressive neural architecture search is given very good results. We wanted to try that trick of parametric sharing among sample architectures and see if we could do good as well, if we could do well as well in IPNAS. But the main problem that we wanted to tackle is the intrinsic greediness of progressive NAS. We don't want to trust the surrogate function so early during exploration. So we better start with a more random exploration, so the surrogate function is able to see a bit better how the search space behaves, and then transition slowly to a surrogate-based sampling. So basically, we can set up change the greedy top K selection by peanuts and just basically do random sampling based on the score of the architecture. But we also include a temperature-based computation, so we can control how random is the exploration of the search space. So we start first by having a more uniform distribution, and then fully trusting the surrogate function at the end during exploration. So to do that, we include iterations over the progressive neural architecture search. And basically, we are relaxing the role of the surrogate gate by using it as a predicting sampling probability instead of directly predicting the top K architectures. So the weight sharing trick is very simple. As we bring it to peanuts, basically, suppose you have sampled this architecture, you train it for a few epochs, then you want to train this neural architecture then, but you can see that actually there are two elements that are shared among them. These two elements, instead of training from the very beginning, you basically just bring the weights from the previous training that you did. The same happens from a new neural network that you are sampling. Basically, if you try to see which elements you already trained, and load the weights, bring them to the process. So this is basically our algorithm, and I wanted to show you a few results. The first one, it's a fair comparison with progressive neural architecture search to see if actually we are improving over them by doing these two tricks. So, and apparently we do. This experiment was done in the macro search space. It's a very small experiment, because if I were to reproduce what they did in the original paper, I would need a lot of resources that I didn't have. So basically, I'm just reducing the problem to search a neural architecture on CFAR by only using sampling 10 architectures with a maximum depth of 5 layers, and 4 operations for each layer are the maximum number of operations that I can choose from. So you can see that the error for us is actually it's way smaller, but we are also way more efficient. It took a third of a day to find this architecture, whereas it took them almost a week. This experiment was done on our lab, so it's our own progressive neural architecture search implementation, so maybe it could be a bit faster, I don't know. On the other hand, these are results for the state of the art. These are as the results that are given in the original papers. So in the first group of methods, you can see a baseline of designs that were, well, designed by hand, by human experts. And on the second line, you will see results for the macro space. And on the third group, you will find designs for the micro space. So it's interesting to see that in the macro space, you are able to beat, for instance, efficient neural architecture search that it was a state of the art at some point, and we are just slightly slower. They took them half a third of a day, and for us it was only 1.2 days. So for the micro space, we don't really reach the minimum, the smallest results, but we are definitely more efficient than progressive neural architecture search, while staying not that far from them result-wise. And this is the kind of architecture that we found in the macro space. So a lot of skip connections. Actually, that corresponds a bit with the state of the art, where it was found that skip connections are very good for classification problems. And in the micro space, we found this architecture. It's also interesting to see that we found architecture with so many identity connections in the blocks. That means that the cells that we found are not that heavy, since there are no parameters in those identity connections. We didn't include any term that was explicitly modeling reduction of the optimization of the size of the neural network. It just turned out to be like this. And of course, this is just the cell. At the bottom, you can see that there is we found a full convolutional neural network by stacking a lot of these cells. In conclusion, we found out that relaxing the role of the surrogate function, so it predicts sampling probability to allow IBNAS to alleviate intrinsic greediness of progressive neural architecture search. We also found out that search iterations together with temperature-based sampling helps IBNAS work well with weight sharing. And finally, IBNAS was able to find really good architectures in comparison with the other methods. So, thank you.
Okay, questions?
The surrogate function, you mean? That's a neural network. It's a recurrent neural network, to be exact. It takes the sequential description of a neural network and outputs a prediction of the score on the validation dataset. Meta, maybe. Haven't thought about it, really.
Do you find any common features in the searched architectures among any papers? Like, there are many papers using the neural architecture search, but do you find anything common in between the final architectures?
I didn't go and check the kind of architectures that they found, and that would be an interesting thing to do, so I have to say no. But there is something that really is different on the kind of architecture that we found, and it's the fact that we had so many identity connections. So, okay, you were asking for similarities. Actually, I just can't point out a difference. Yeah.
Maybe I can ask a question. Do you have any model complexity reduction in terms of the size of the model?
No, we don't. We are not including. We are not modeling that part. The interesting thing is that the method itself is agnostic to the score that you're maximizing, so we could include it as well. It's just that we didn't do it for this paper. Yeah.
Okay, let's thank the speaker again. Okay, we will have the last presentation for this session. The speaker is from Boston University, US. Okay, please go ahead.
Hi everyone, my name is Vitaly, and today I'm going to talk about RISE. It's a work done in collaboration with Abir Das and Kate Sayenko at Boston University. So RISE is a tool for analyzing the black box models. A lot of time working with neural networks, we end up wondering what's going on inside of them and how can we get more insights on why they perform as they do. For example, here you can see an image that is being classified as a line with high confidence. And an interesting question to ask here would be, what makes this image look like a line to the network? Is it just the adult lioness, or the cap contributes as much? What about the reflections? Does the model see the line there? And these sort of questions can be answered by looking at the importance maps or saliency maps. For example, here, by looking at the importance maps, we can say that the most important region of the image is lioness face. Obviously, this is not the only type of questions you can ask to try to understand the model better. For example, you can look at what substitutes a category for the model by doing activation maximization or by generating iconic images. Also, you could try to find some separate neurons that are responsible for semantic concepts by using network dissection, or you can just try to develop a more interpretable model in the first place. In this case, you will be able to better understand the model by just looking how it performs. And all this kind of research can be generalized as explainable artificial intelligence, and a lot of work is being done in that direction. So in our work, we focus on saliency maps, and they come useful not only for image classification, but in a variety of tasks, such as image captioning, activity recognition, sentiment analysis, any task where you would like to see how, what regions, what parts of inputs are more important. And again, a lot of work has been done in that direction, but most of them fall under the white box model approach. That is, when you have a full access to the model, you are able to see and access the weights and gradients, and you can use them to produce saliency. And not so much work has been done for black box models. In this case, you're only allowed to feed the inputs into the model and observe the output. You cannot see what's happening inside. And existing work have some drawbacks. For example, sliding occlusion would fail if you have multiple salient objects in the image. And LIME relies on superpixels, so it cannot highlight arbitrary parts of the image. Let me walk you through our approach. The idea is really simple. So given a black box model, for example, an image classifier that we would like to explain, and given an image I and a category that we want to see the explanation for, here we are looking for the explanation of shark, what we do is generate a bunch of random masks, M, and we apply them to the image by using element-wise multiplication. Then we feed the masked images through the black box model and observe the scores they produce. We do it for many generated masks, and every time we observe the probability. After that, we simply average the masks with respect to their weights, to their scores, and treat the result as a saliency map. So the idea why it should work and why it actually works is the following. Every mask determines what regions of the image to keep and what regions to discard. And whenever the mask keeps something important in the image, we expect it to have a higher score. And as a result, the score, since the score is the actual weight of the mask, more important masks will get a higher weight in the sum. So in the end, we have a saliency map that keeps some important regions of the image. In our work, we show that the saliency that we get using this approach can be defined as following. This is the expectation of a scores of a randomly masked images, conditioned on the fact that the region, so the saliency for region lambda, is an expectation of a scores produced for randomly masked images, conditioned that this region lambda is preserved by all the masks. So from here, we use two approximations to get to our final method. First one is that we go from binary masks to continuous. There are two reasons for that. First one is that we would like to get rid of sharp edges in the masked images. And the second reason is that using continuous masks, we get smoother saliency maps. And the second approximation we use is that we are not computing expectation properly. We are just sampling the small fraction of possible masks. So that results in Monte Carlo approximation of that expectation. Just a couple of words on how we generate our masks. So we start by generating some smaller size binary mask, and we upsample it to higher than image resolution, and then we randomly crop the image sized region from that. And we do this multiple times to get the number of masks we need. Our method allows to produce explanations for any category allowed by the model, and this is all done in one pass. So after one pass of the architecture I showed you, you will get the explanations for all possible categories. Okay, so now that we have saliency maps, how to evaluate them and to tell if they are good or not. Let me first show you a couple of examples. So this is the data from Functional Map of the World. It's a satellite imaging classification challenge, and we just took the data and their pre-trained model, and we run our approach to analyze the model. And we can see, for example, in the upper row, that model focuses not only on the power generator, but also on its shadow to predict the wind farm class. And in the bottom row, you can see that area shadowed by the trees is less salient for recreational facility class. These examples prove the point that sometimes good explanations don't align well with human-labeled ground truth. In both cases, if we were to compute some localization metrics, the saliency maps will not get high scores, but they're still a good explanations, and we can see that shadows are important. That's why we tried to invent some metrics that would capture how well the saliency maps show the causes in the image for the prediction. So we introduced two metrics. First is called deletion, and the way it works is the following. You have an image of a tasker. In this case, it's a kind of elephant, and you have an explanation for the class tasker. And what you do to compute the metric is you start removing salient pixels one by one. First you remove the most salient, then the next one, then the next one, and so on. And all this time you observe how the probability for the tasker class drops. You do this all the way till you get the completely gray image, and you compute the area under the curve for the final score. So the better the explanation is, the sharper the drop should be. That's because if you remove some important regions in early stages, that means the explanation is good. So the less area under the curve, lesser area under the curve means steeper drop, and it means better explanation. Similarly, we define the insertion metric. In this case, you start with the blurred version of the image, and you start deblurring pixels according to their saliency. And in this case, we expect the probability to go up, and the AUC should be higher. So in terms of these two metrics, we evaluated our approach compared to two other black box methods and one white box method. And we outperformed all of them for two architectures, ResNet50 and VGG16. That was done for ImageNet's validation dataset, parts of the dataset. And also we computed the metrics, the points in game. It's a localization-based metric for two same architectures, VGG16 and ResNet. And for VGG16, we still outperform other methods. And for ResNet50, we place about third. We also we've put up a demo online, so you can go and see the explanation, the saliency maps, and the intermediate steps for the evaluation. So to conclude, we introduced a new approach for explaining black box models that is not dependent on the model. It can be any architecture, any framework. You can analyze proprietary models. And we also introduced two new metrics to evaluate the causal performance of the saliency maps. This is it. Thank you.
Any questions? Yeah, please.
Sorry, I didn't hear the last part. So the color of the mask, you mean the gray color? The gray color occurs because you multiply the image with a 0 to 1 mask, and the 0 corresponds, basically, it's the average color of the data set. We didn't try anything else, it's just multiplication with 0 to 1. So 0 makes its mean color of the data set. So it's not we didn't pick any color. Sorry, I can't hear you.
In order to get the desired performance, will it be a computational bottleneck in real time?
Right. So the number of masks we used in our experiments was from 4,000 to 8,000. So that's for every image. It is a bottleneck for performance, but it's a sacrifice that occurs for explaining black box models.
white box approaches, they do have access to internal parameters. They can do it real time. But when you're trying to analyze black box model, you only have the opportunity to manipulate the input. So yeah, the training time, the time is an issue, but it's a sacrifice.
You show that if you erase some part, just a slide.
Mm-hmm.
But to my understanding, if you erase more parts, the score should, just to my understanding, it should keep decreasing. But sometimes it increases. Can you explain why?
Yeah, so sometimes the score increases. Like here, you have another peak. That has to do, first of all, with the softmax. It always produces the probability sum to 1. So some categories can always be high. And the other issue is that with these explanations, you always have to deal with adversarial effects. And sometimes, yeah, as you can see, some image that has a lot of weird gray parts, it still classifies like 40% tasker. So sometimes that happens, like in this case.
Thank you.
Any more questions? Okay, great. So we are pretty much on time. Let's close the session.
And thank all the speakers again for their nice talks. See you tomorrow.